Hello, everybody. Welcome back to Mathematical Statistics. That is Rufus. And I don't know if you noticed, yeah, Rufus has no eyes. So I love to let his hair get really wild and have like quote unquote Karens come up to me in public and complain that my dog's hair is in my eyes and needs to be cut. And I'm like, what eyes? Anyway, that's Rufus. So I called him in because I think I need a little help today with one of these proofs, and he's pretty good at it. Welcome back to Mathematical Statistics. You do have a new homework coming out within minutes after the class. I just finished writing it, but I still need to post it. And yeah, I think you're going to like it because it's going to be lots of kind of computational stuff like MLEs and MMEs and well, actually, I don't know if you're going to like it, but I think it's going to be fun. So let me share my screen. We were talking about the Crimera lower bound, and this was part of a big diversion from MLEs, from maximum likelihood estimators. Okay, so here we have in our setup x1 through xn, and they might be IID, but they don't have to be. So I'm going to say a little more generally with a joint PDF, f of the vector x and theta. And so far, actually, our Crimera lower bound that we've talked about is only for one-dimensional theta. You know, we're taking derivatives with respect to theta, and we could take like vector value derivatives, but we certainly didn't prove that kind of thing with Cauchy-Schwarz. So there is a higher dimensional Crimera lower bound, but for now, let's assume theta is one-dimensional and not in the indicator because the Crimera lower bound fails there. Not in the indicator for the PDF for the distribution. So our goal is we want to estimate some function of theta, which could be theta itself. Want to estimate tau of theta. And we have some estimator, which usually we would call tau hat of theta. But that is going to be some kind of statistic, which is a function of the data. So I'm shifting notation just a little bit. And let's say we have a statistic. Again, that means a function of the data. I'm going to call it T. It's capital, random, just like, you know, it could be X bar or something, but it is a function of capital X1 through capital Xn. And the assumption here is it is unbiased for tau. So it's an unbiased estimator for tau. So the Crimera lower bound says that the variance of T, and I did this last time as well. I want to change have a statistic. It technically works, but I want to really emphasize any statistic. Every unbiased estimator of tau, the variance is bounded below by this thing that we're calling the CRLB for tau of theta. And we defined this last time as the derivative tau prime of theta squared over something called the Fisher information. I denoted that with an IN of theta. That's actually a pretty common notation where IN of theta is the expected value of the derivative. Actually, doesn't matter, but I like partials in here. The derivative with respect to theta of the log of f of, so this is the joint PDF, and the expectation won't make sense unless there's some randomness in here. So we're plugging in the random variables into the joint PDF and squaring this whole thing. Okay, so this is the, yeah, as I just said, Fisher information. Okay, and so we proved this using the Cauchy-Schwarz inequality and a couple of clever moves on rewriting some things. And then I went into a list called computational simplifications for the Fisher information. And we were on our second thing in the list, although I did label them 0 and then 1. Simplifications. I'm not even going to write 0 here because that's not one of the simplifications. That just helped us prove one of them. And actually, this one really isn't a simplification. So it's an alternative way to compute the Fisher information, and it might be easier. So that was that this Fisher information can be computed as the negative expected value of the second derivative with respect to theta of the log of f of x and theta. And I can't remember if we got to use that last time. If we did, it was at the very, very end. But often you'll end up with something like, I'm just gonna not redo this whole thing because I think I did it. In the exponential distribution case, you end up with x minus 1 over lambda squared for your Fisher information term, which is a variance term. But this is the derivative of the log of the PDF. And the second, I don't know if anyone has notes in front of them. Tell me if I did the second. I know we got into this exponential example, but I don't know if I did the second derivative. So the second derivative here with respect to the parameter, in this case lambda, is going to be positive 1 over lambda squared. Positive. Sorry, without the square. Ugh. Let me just do it. I'm making a mess out of trying to just bring up part of it. So quick example. I know we did the Fisher information the kind of longer way for this example. And if we did this one already, let me recap. Okay, so the f of x and lambda is lambda e to the minus lambda x. Yes, an indicator, but I'm not going to drag it through. It just kind of will always sit there on the side. Remember when we talked about piecewise defined functions and how you take the derivatives and the logs of the function, but not the parts defining the pieces. So we get a joint PDF, which is lambda to the n, e to the minus lambda, sum of the x's. The log of the joint PDF is n log lambda minus lambda, sum of the x's. The derivative with respect to lambda of the log of the joint PDF is n over lambda minus the sum of the x's. Oh yeah, the example I was trying to do in that little corner did not make sense at all there. But the Fisher information, one way to compute it is to square this and take the expectation. And since this thing is squared, we could change the order. And if we change the order around, rewrite it this way, then we see a sum of exponentials, which has a gamma distribution. In particular, the distribution is gamma n comma lambda, and the mean of the gamma alpha beta is alpha over beta. So this is the mean of the gamma, and this is the variance of W, where W is gamma n lambda. I know we got through that. That's why I'm rushing this one. And then, yeah, if you look up the variance, it's alpha over beta squared, so n over lambda squared. So that's just a Fisher information computation. This theta at the front should have been a lambda, or unless you just want to say it's standing in for my generic parameter, but that's not what I meant. So this theta with this big underline should have been a lambda. Okay, so just so we don't forget that there's a computation that this is only a part of the Crumérat lower bound for lambda. So tau of lambda is lambda itself. And if you take the derivative, you get 1. So this Crumérat lower bound is tau prime of lambda squared over the Fisher information. And that is 1 squared over n over lambda squared. So that is lambda squared over n. But using this new computational simplification, I can go on from this derivative. And so the second derivative, so I'll just say also, this is just another way to do it. The second derivative with respect to lambda of the log of f of the vector x and lambda. Let me stop writing theta. And lambda is, so my first derivative is currently at the very top of my screen. And you'll see over here, if I take the derivative again, so I take the derivative of this with respect to lambda, and the sum of the x's is constant and disappears. And here we have essentially a lambda to the -1, so you get negative lambda to the -2. In other words, we get minus n over lambda squared. So the n-dimensional Fisher information is the negative of the expected value of this expression. And the cool thing about this is that it is greatly simplified in the sense that there are no x's left. This is a constant and non-random. So we get negative expected value of negative n over lambda squared. And that is the negative of negative n over lambda squared. There's just nothing random there. So the same thing we got the other way we computed the Fisher information. And that was much, much simpler. Well, I don't know how you're feeling about that, but there was no expectation to take. So pretty cool. Okay, so please stop me or ask me to scroll up or anything like that, but I'm going to go on to computational simplification number 2. Nothing we have done so far in the Cruméra lower bound setting has required that the x's be IID. We're starting with some joint PDF, but if they are IID, things get a lot easier. Things simplify. So this one truly is a simplification. So if x1 through xn are independent and identically distributed with the single PDF that they share, f of x without a vector, semicolon theta, then this n-dimensional Fisher information, why do I say n-dimensional? It probably doesn't make any sense right now, but the definition of the Fisher information involves a log of a joint PDF, and that is a joint PDF with n x's. That is an n-dimensional joint PDF. And if you only want to use one x in that computation, that would be, like a vector of length 1, a one-dimensional Fisher information. And in fact, if these are IID, you can get this Fisher information by taking n times the one-dimensional Fisher information. We're going to prove that, but scrolling back up, you're going to have to compute something like this, but you're only going to have one x. So you won't have to deal with a sum of random variables, or maybe even a weirder combination of random variables. Because although we really know that the sum of exponentials is gamma and the sum of normals is normal, there aren't that many sums that we know the distribution of. So it would be nice to deal with only one random variable and not all n of them. Okay. By the way, you can do this either way. So this is the expected value of the derivative with respect to theta of the log of f of a single x. I'm going to write x1. Sometimes I like to write just an x, but it's not any one of them. It's just a representative. Maybe writing x1 makes it a little more clear, or x5, any one of those. Or we can take the negative of the expected value of the second derivative. So let's prove this wonderful result. Proof. Okay, I'm going to start with the n-dimensional Fisher information. I'm going to start with this left-hand side and see if we can get to the right-hand side. And I think this is going to be, I don't know if it's going to be easier. I'm going to use the first original representation of Fisher information. So the expected value of the derivative with respect to theta of the log of the joint PDF, and all of that inside the expectation gets squared. Now, because they're IID, that joint PDF is a product of individual PDFs. So because these are IID, this is the expected value of the derivative with respect to theta of the log of the product as I goes from 1 to n of f of xi and theta, and then that whole thing gets squared. This is a sum of logs. The log of a product is a sum of logs. And I think that, well, I'm going to do two things here. I'm going to bring the product outside of the log and turn it into a sum, and also bring the derivative inside the sum at the same time. So this is the expected value of the sum as I goes from 1 to n. Absolutely no problems with that here because it's a finite sum, so you don't have to worry about not converging when you pass the derivative through. The log of f of xi and theta, and that whole thing is squared. So if you write that out, I'm sorry, this is going to be really insulting to some of you, but I always find a few people outside of math and applied math that this helps. So I am going to write this as two different sums, and so as not to confuse the term, two different indices. And then I'm going to pull this whole constant inside this sum. And so this is the thing I thought might have been insulting to some of you. A sum squared is a double sum. And actually, I have no idea how you feel about that. So let me know if that doesn't make sense. But this is the same thing as the sum as I goes from 1 to n, the sum as j goes from 1 to n of the derivative with respect to theta of the log of f of xi and theta. Nice finite sums, so I don't have to worry, but it seems like I don't worry anyway, even if there could be convergence issues. Let's pull those sums out. And I lost one of my logs. Sorry, I lost a whole derivative. So I need this ith derivative and the derivative of the jth part. But now I'm going to pull the sums out. I goes from 1 to n. J goes from 1 to n. Expected value of that product. So the first of the two terms here is just a function of xi, and the second is a function of xj. And so whenever I is not j, and that's a whole lot of terms here, right? So if I is not equal to j, we have the expected value of, I'm not going to write it, unless, I don't know. Let me know if it's too confusing. We have this expectation, and this one has an xi in it, and this one has an xj in it. And if I is not j, then we have a function of two independent, we have a function of one random variable and a function of an independent random variable. So by not IIDness, by independence, this would break up into the individual things in a product. And each of those, that's the expectation of the score function. By computational simplification number 0, both of those are 0. So a whole lot of terms in this double sum are 0 every time I is not equal to j. Does that make sense? Was I too sloppy on that one? Okay, so I like to think of double sums terms as organized in an n by n matrix. And so we have an expectation in every entry of that matrix, and everything off the diagonal is 0. And then everything on the diagonal, when I equals j, we're going to have this guy squared. And they're all IID, so we're going to get that over and over again. So we have n terms like the expected value of the derivative with respect to theta of the log of f of xi theta, and then the same exact thing, which of course you can write as a single expression squared. And I will. But that is how we define the one-dimensional Fisher information. Because that is exactly our Fisher information, except we don't have a vector in there. Okay, so way too many boards went by here, but we had I and theta. Don't worry, I'm not going to rewrite that whole thing, but we had this double sum and we had some terms that we needed to take expectations of. And we saw that all the terms off the diagonal are 0, and all the terms on the diagonal are this same thing, and there's n terms there. So we get n of these guys. And the other terms are all 0. And that's what we wanted to show. So that's pretty awesome. So in the exponential example, we had that the log of the PDF was the log of lambda minus, oh, what did we do? Oh, I showed you a second derivative example. Okay, so the log of the PDF was the log of lambda minus lambda x. This is a one-dimensional kind of thing. And the derivative with respect to lambda of the log of f of x, no vector, is 1 over lambda minus x. And so the one-dimensional Fisher information using our first formulation is the expected value of this thing squared when you plug in a capital X. Square it. So that is the expected value 1 over lambda minus x1 squared, which is, no, you don't need to write this line, x1 minus 1 over lambda squared. And because this is the mean of the exponential distribution, this is the variance for x1. And for the exponential, that is 1 over lambda squared. And so the n-dimensional Fisher information, because we have IID random variables here, that is the assumption. I didn't really write the whole example very well, but it's n times the one-dimensional Fisher information, and that is n over lambda squared. And that's the same thing we got now for the third time. And we also could have done this with a second derivative, which would again give you the nice, easy. I mean, this was really not hard because we already know these quantities, but if you did the second derivative with respect to lambda, you would get in this problem constants. And so the expectation would be super, super easy. Okay, I was going to do some other examples because I'm always doing the exponential, but I think I think I should move on because the Crimera lower bound is very routine, right? Write the PDF, take the log, take the derivative. We're going to have plenty more examples within what's coming up next. So I'll skip the pure Crimera lower bound extra example. But we are now finally ready to talk about the large sample properties of MLEs. So I'll call this the great and mostly large sample properties of MLEs. Maximum likelihood estimators. I'm going to need a little notation here. So I've got I'm trying to decide if I want to do a list, if I want to keep stuff IID or not, because I can have a longer list. Let's do IID for now. So suppose that x1 through xn are IID with the common PDF f of x and theta, and let theta hat be our MLE. But because I want to like sort of let n run around here, like take some limits, I am going to put a sub n. So I'm going to let this I'm going to let it be n MLE, A maximum likelihood estimator. I never know what to do there. It's n MLE, but it's A maximum likelihood estimator. B MLE. Okay, for theta. So usually we don't have an n on there, but you know how sometimes I write x bar versus x bar sub n to really stress that dependence? Okay, so under certain regularity conditions, we are going to uncover these as needed, but 3 of them are the same conditions needed for the Cramér-Rao lower bound. And that was that you can interchange the derivative and the integral, and that the derivative of the log exists, and that the Fisher information is greater than 0 but finite. So under certain regularity conditions, we get some cool things. So number 1, we get that the MLE exists and is unique. And I'm not going to prove this one today because it's not really anything specific to math stat. And there's so many different sufficient conditions here. So for example, if your likelihood is continuous and your parameter space is compact, then there is going to be a maximum in there somewhere. So you're guaranteed existence, and I could give you lots of little, like, not really general advice. You really just have to look at your particular function and figure out if it has a maximum or not. Um, there's lots of kinds of sufficient conditions I could give you. Okay, so a little more interesting maybe is that theta n hat converges in probability to theta. And the other way to say this, of course, is that theta n hat is a consistent estimator for theta. The next thing is that theta n hat is asymptotically unbiased. And this means that, it may be actually unbiased to begin with, but if not, it will be unbiased in the limit, in the sense that, i.e., the limit as n goes to infinity of the expected value theta n hat is going to be theta. We saw MLEs already that were biased. Some of them are unbiased to begin with, and in which case this expectation would be theta all the way through the limit, which is fine. Not going to affect this statement. The fourth thing is that MLEs are asymptotically efficient. This is something we defined efficiency last time. I'll remind you what that is. So this has to do with the variance getting down to that Cramér-Rao lower bound. This means that the limit as n goes to infinity of the Cramér-Rao lower bound for the variance of all unbiased estimators of theta over the variance of the MLE, that this is going to go to 1. On the way to 1, we're not guaranteed that this is less than 1, because the Cramér-Rao lower bound only really applies for unbiased estimators, which MLEs are not necessarily unbiased. And if the estimator is unbiased, the variance is always larger or equal to this. So with an MLE, this variance could actually be smaller than this, but the MLE would have to be biased, but it would go to 1. So we would like, it's kind of like having the best variance in the limit. And so the larger and larger sample you have when you're doing this with data, the better you can feel about your estimator in terms of it having small variance. Final one, at least for today, is that they are asymptotically normal. In particular, the MLE for theta is asymptotically normal. It has the correct mean, and that is what we're trying to estimate. That's the mean, theta. And the variance, sort of suggested by the property right above, the variance is going to be the Cramér-Rao lower bound for theta. So a Cramér-Rao lower bound, again, isn't going to make sense for an MLE for a fixed sample size, but when things get large, it just turns into unbiased and lowest variance kind of stuff, which is why people love MLEs. I like, oh, yeah, okay, I'm going to show you all the dog hair on my shirt. Wait, this is totally worth the time to reshare. I don't know if it's backwards, but got my Umvu shirt on today, even though it's not Umvu day. Yeah, you're like, what's that? So you have to install a plugin. Okay, so I said we were going to prove one only because all I could possibly do is give you a big long list of, well, when does a function have a maximum and when is it unique? There's nothing really special to statistics there, but let's look at two. Actually, I don't want to prove two either. I want to prove the ones that you'll get something out of that can help you with other problems. So if we prove two, we will leave knowing how to prove two. It's not really gonna, there's other ones that'll give us skills that we can apply to other problems. But there's something in two that I do want to mention. It's important to know. So for the proof of two, we're going to need, which we're not doing, but we need this inequality in general in statistics. We need something known as Jensen's inequality. So Jensen's inequality. I don't think we did this. Please stop me if we did back when we were talking about convergence and probability and different inequalities. I think we just did Markov, generalized Markov, and Chebyshev. So this says that for a convex or concave up function, g of the expected value of x is less than or equal to the expected value of g of x. That's prelim material right there. You should tuck that away for future use, but I'm not gonna use it because I'm not gonna do this proof, but let's prove Jensen's inequality. So proof of Jensen. I'm gonna start by just kind of looking at it. If I graph G, it's convex, or concave up. And I'm gonna let mu be the expected value of x, and that is just a number. So that's somewhere on the x-axis. Let's say it's right here. And then the point from G is G of mu. And because it's convex or concave up, if I make a tangent line at that point, that line will always be below G. I sort of curve that at the end to get it out there. So this line has the equation, or an equation like y equals some slope and then x minus, and I can use the point mu comma g of mu to describe this line. So x minus mu plus g of mu, or sum for some slope that I don't even care about. So since G is convex, then G of x is always, so that's not the order I want. Well, I'm sure you can handle it if I write it in the opposite order, but I'm going to start with the line. The line is always below G of x. So the m x minus mu plus G of mu is less than or equal to G of x for all x. For all x. And so if we're going to plug in a random x, that will still hold. So let me make these capital. X minus mu, G of mu less than or equal to G of capital X. And now I'm going to take the expected value on both sides. Ooh, I guess I guess we don't know that that holds, do we? Maybe I'll add that in today's homework. This is already an aside. If x is less than or equal to y, does that mean the expected value of x is less than or equal to the expected value of y? It absolutely does. But what does this even mean? If they're random variables, how is one going to be less than or equal to the other? When you see something like this, that is a with probability 1 statement. You know what? I will either, let's talk about it next time. If not, I'll type it up for you. Okay, so taking the expectation through on the left side, we get this m, my slope, the expected value of x minus mu, plus the expected value of g of mu is less than or equal to the expected value of g of x. And when you run the expectation through on this first term, you get mu minus mu. So that first term is 0, it goes away. And I can't even read this. The expected value what did I do? Expected value of g of x. Oh yeah, okay, sorry. So g of mu is a constant. There's nothing random there. And so the expected value of g of mu is just g of mu. So I get 0 plus g of mu less than or equal to the expected value of g of x. And in other notation, this is g of the expected value of x less than or equal to the expected value of g of x. And that's what we were trying to show. So if your function g is concave as opposed to convex, or another word for that, another word slash words is concave down, the inequality goes the other way. And to show that, you can just say, if g is concave down, the negative of g is concave up. Apply Jensen's inequality, and then like multiply both sides by -1. You'll just get this going the other way. Is everybody okay? Okay, so we were in the list of important and large scale properties of MLEs. And the second thing was that it's a consistent estimator of theta, which means it converges in probability to theta. And to prove that, you could check it out in the notes. You would use the weak law of large numbers along with Jensen's inequality to get some of those probabilities, bounded, the probabilities that you need to look at the limits for convergence in probability. But I'm going to skip the proof because I think there's proofs that you can get more out of. So the third thing is the asymptotically unbiased. By the way, I'm hiding some of the regularity conditions in here. To get that convergence in probability, I said that you would use Jensen's inequality and the weak law of large numbers. But in order for the weak law of large numbers to hold, you need the variance of the MLE to be finite. So like that would be a condition. For asymptotically unbiased, there's multiple ways to get asymptotically unbiased. The easiest, I think, the easiest sufficient conditions, because this list sort of mostly holds, would be to have that theta n hat, the MLE, is converging in probability to theta, and that's going to require a finite variance so that you can use the weak law of large numbers. And the variance of theta n hat less than or equal to a constant. And this is for some constant m, and it can't depend on theta. I don't know if that's clear when I say it's a constant. Maybe not, because when I say constant, I mean non-random. So I want to emphasize that doesn't depend on theta. Okay, so let's prove it under these conditions. And in the proof, I think we've already done this. We talked about, I'm pretty sure we've talked about the expectation of an indicator being the probability of the thing being indicated. Does that ring a bell to anyone? Like Or I'll just do a quick refresher. The expected value of the indicator of the event that X is greater than 3. I don't know if we did this. So I'm indicating that that event happened. It's 1 or 0. You're probably a little more used to a notation like this. It's meaning the same thing, but I think this notation is easier to read. We're indicating whether or not that event happens. And no matter what, if the random variable X could be continuous, but the indicator is always discrete, taking on 2 values. So this is going to be 0 times the probability the indicator is 0 plus 1 times the probability the indicator is 1, which is going to leave us with the probability the indicator is 1. This is a great trick often used in probability and statistics. Now that indicator is 1 if and only if the thing being indicated happens. So this is equivalent to the probability that X is greater than 3. So what I was saying at the beginning was the expected value of an indicator is always equal to the probability of the event being indicated. We're going to need that in this proof. I don't think we're going to get to this today, but I went through the trouble of making a poll. It's anonymous. And wow, we're interacting. It's anonymous, but I have some arguments coming up that involve little o, which is analysis type stuff. Okay, so back to the actual proof here of asymptotic unbiasedness. So I'm going to look at we want to show that the limit let's consider the absolute value of the expected value of the MLE minus the true value of the parameter. I want to show that this is getting small, right, as n gets large. Okay, so I am going to bring that theta, which is a constant, inside the expectation. Nice. Okay, I'm going to bring the absolute value inside that expectation. There's several arguments to be made here. One is that it's like an integral, and you maybe know what happens there. Another is Jensen's inequality, using g of x equals the absolute value of x. Another is kind of common sense-ish. This is going to be less than or equal to the expected value of the absolute value of this difference. Why? Because expectation is a kind of average. Yeah, it's probability weighted, but it's still an average. And so if the absolute value is outside, the quantity inside could take on positive and negative values, and maybe the average would be, I don't know, they'd be canceling each other out. But if you make all the values positive and average those, it's going to be larger. So 3 arguments. One is just kind of intuitive, one is Jensen's inequality, and one is probably something you already know about, like integrals, inequalities. Okay, so check this out. This is a trick we're going to use. Oh, don't say trick. A method. Right? Math is not about tricks, but it's about pulling cool methods out of your back pocket. So I'm going to rewrite this. This is from here, but I just want to get out of the column problem. I'm going to write this as the expected value of the absolute value of theta n hat minus theta times the indicator of the event that says that the absolute value of theta n hat minus theta is less than or equal to epsilon, plus, I'm going to erase this, plus the absolute value of theta n hat minus theta times the indicator of the other event, which is saying that the absolute value of theta n hat minus theta is greater than epsilon. I'm breaking this into 2 pieces, kind of like, well, not really like breaking into a positive and negative part, but those are do you buy that? All right. This is equal to the expected value of the first term plus the expected value of the second term, just linearity of the expectation. Now this first term, this indicator is 0 or 1, right? It's bounded above by 1. And when that indicator holds, the thing being indicated is telling me that this piece is bounded above by epsilon. So this whole thing is less than or equal to epsilon plus the expected value of the second piece. Okay, so this is going to be a little strange. I'm going to rewrite this. I got to close that bracket. I'm going to square the expectation and then put a square root on it. Why am I doing that? I am setting us up for a Cauchy-Schwarz maneuver. Expected value of all this stuff, theta n hat minus theta greater than epsilon, and then all of that squared. And I didn't close my square bracket inside. So here I have an expectation of something squared, and by the Cauchy-Schwarz inequality that we did last time, this is less than or equal to the expected value of the individual thing squared times the expected value of the other individual thing squared. So this is less than or equal to, I'll put CS for Cauchy-Schwarz, epsilon plus the square root of the expected value of theta n hat minus theta squared. I did drop the absolute value because it's squared, times the expected value of the indicator squared. But that's not all that interesting because an indicator is 0 or 1. So I get to drop this, and I don't want to waste a whole line writing that. There's a squared here, but because this only takes on the values 0 and 1, you can drop the squared. Okay, we're almost done. This is equal to epsilon plus a big square root. Now this first thing is the second expectation. Let me do that while we're at it since I can, is the expected value of an indicator. And that is the probability of the event being indicated. All right. Well, that was a letdown, and I can't seem to let it go. I'm going to let it go. Okay, so we're proving hopefully proving some properties of MLEs and mostly large sample properties. The next one was asymptotic efficiency. We can get that out of the fifth one, which is asymptotic normality. So let's do that first. And then next time, clean up with asymptotic efficiency. And then we're going to start material for the MVU, which is still a ways away, but machinery for the MVU starting next time. So let's talk about the asymptotic normality of MLEs. The regularity conditions were things I was going to list as I went. I can tell you ahead of time here that we're going to need some strange things, like not strange, but they're not nice conditions. They're so specific, like the third derivative of the log likelihood is bounded. Things like that would be in any list that anyone would put up in front of a list like this of properties for MLEs. So the claim is that the MLE is asymptotically normal with the correct mean and then the variance getting all the way down to the lowest it could be. And to prove this, this is very similar to something else we proved. I don't remember what that was, but we used a little Taylor polynomial on the likelihood, or actually the log likelihood function. Maybe we didn't. I might be confusing that with another class. So I am not sure if I made these IID at the beginning. I did make the list IID at the beginning. So some of these properties I don't need IID for, but I do need it for this asymptotic property. So, okay, let's prove it. I need to change the notation up just a little bit because we're going to be working with likelihoods and derivatives of likelihoods and limits of likelihoods, and likelihoods we write as a function of theta. But theta is supposed to represent the parameter that generated the data. So let's suppose we have x1 through xn IID with some PDF, f of x and theta. If I just leave it like that, it's going to be confused. So that's supposed to be a specific value that generated the data. That's a number, but there's going to be thetas floating around in likelihoods here. So I'm going to call this theta naught. And this is just to make it really like special and specific, as opposed to a theta as an argument of a likelihood function. Okay, so recall you can get a Taylor polynomial of a function, say f, if you want to expand it around a point, say c, and have one or two terms. You can write any f, well, not any, it's got to be nice enough, but you can write f of x as some f of c plus an f prime of c, x minus c, plus 1/2 f double prime of c times x minus, that c should not be there because I want to cut off this polynomial right here. I want this to be my final term, which means instead of that c in there, I need something else. I usually use a c, like a x, whatever, a squiggly thing, x minus c squared. And this is going to be for some c between 0 and c. So I want to use this, but I want to take the f to be the derivative of the log likelihood. So we will use f to be the derivative of the log likelihood. So that's my kind of lowercase script l. That's the log likelihood and one derivative. And I'm going to take x to be the MLE. And I'm going to let c be the actual specific value that generated the data. And so if you rewrite the Taylor polynomial with this stuff, so obviously you need the log likelihood to be differentiable. This is one of many so-called regularity conditions. But we get L prime of the MLE equals L prime of theta naught plus L double prime of theta naught times the MLE minus theta naught plus 1/2 L triple prime. So we need L to be 3 times differentiable. And sometimes I'll say, well, only to get this proof done, but maybe you can prove it in another way. But you actually need the log likelihood to be thrice differentiable, even for, like, I don't know of any way to prove this without this assumption. So in here, I'm going to have something that's between c and x. C is a constant here, x is a random variable. So if that's moving around, the thing in between moves around. And we've done something like this before. I think we called it theta sub n tilde. And then I'm going to finish this off with the MLE minus theta naught squared, where theta n tilde is between theta naught and theta n hat. And again, because this is random, that will make the in-between random because the endpoint's going to be moving around. Okay, on the left-hand side, we have the derivative of the log likelihood with the MLE plugged in. That's 0. That's how we define the MLE. So this guy is equal to 0. It is the derivative of the log of the likelihood. Set that equal to 0 and solve, and that's how you get the MLE. So that should be 0 when you plug the MLE in. Okay, and I'm going to leave this, and shoot. So here's where that little O stuff comes in. In the interest of time, I'm going to be slightly hand wavy here, but I will clean this up at the beginning of class next time. And what is my slight hand waviness? So if we can assume for this proof, I'm going to need theta n hat to converge in probability to the true theta, which is now theta naught. Oh, sorry, I missed that back then. That's a really good idea. Yeah, sorry, I missed the chat about the problem I was having before. So yeah, I'll check it out and tell you if you're right or wrong. I'm sure you're right. So we need this to happen, and we have that as part of our list. But in order for this to happen, we need the variance of the MLE to be finite. So the regularity conditions are like the Fisher information is finite and greater than 0. The derivative of a log of the joint PDF exists. The variance of the MLE is finite. Everything we sort of need to make this work. And this will imply that the other random variable, theta n tilde, is going to converge in probability to theta naught. This is super easy to show, and the reason is because theta n tilde is in between theta naught and theta n hat. So theta n hat converging in probability to theta naught means they're getting close, and this one is squished in between. And if you want to be formal about this, you could say the probability, the absolute value of theta n tilde minus theta naught is greater than epsilon. These are going to be really close together eventually, and they're going to be even closer together than theta n hat and theta naught. So this is going to be greater than epsilon with a smaller probability than the probability that theta n hat is greater than epsilon away from theta naught. So this inequality comes from the fact that theta n tilde is in between. It's closer to theta naught than the MLE. So now if you take the limit on both sides, as n goes to infinity, the right-hand side, if we assume that we have convergence in probability, i.e. if we assume we have the conditions that will get us that, then that second probability is going to 0. And therefore the first probability is going to 0. So that's how we get the convergence of the random variable theta n tilde going in probability to theta naught. Does that make sense? Excuse the scroll. I want to go cut and paste my likelihood equation. Okay, here is the likelihood equation. And let's say we've already zeroed out this left-hand side. So because, okay, because theta n hat is converging in probability to theta naught, as n gets large, locked up. Trying to get my highlighter going. Okay, as n gets large, this term is going in probability to 0. This term is also going in probability to 0, and it's going faster because it's squared. Here's where the little o argument comes in. Basically, both of the things that are currently circled in yellow are going in probability to 0. And the one I care about is the one that goes slower. That's the more important one for determining the behavior of this MLE. So this is something I will formalize next time with little o arguments. But both of these are going to 0 in probability. And this guy in here is going to theta naught in probability. That's what we just showed. And so if that third derivative of the log likelihood exists and is continuous, then this entire term, the L triple prime of theta n tilde, is going to go in probability to L triple prime of theta naught. And this assumes that, again, the third derivative exists and is continuous, or at least continuous at theta naught. The L triple prime is like a G that we're using the continuous mapping theorem on and putting that convergence in probability through that function. Oh boy. This is one of my favorite proofs, but yeah. Next time I try to do something like this, I'm going to do maybe a split screen where I can keep the things we've already proved on the side, because I keep needing other pieces of a very long proof. So here is the basic idea. This we're assuming goes in probability to this. That makes this go in probability to 0 and this go in probability to 0. If this is moving to a constant, and if that is bounded, then this whole term is going away. It's going to 0 in probability, if we assume nice things about the third derivative of the log likelihood. So what I'm going to say in the interest of time is that we basically have 0 is approximately L prime theta naught plus L double prime theta naught, and then the MLE minus theta naught. And this is kind of negligible because it goes to 0 fast enough, but I want to formalize that next time. So what can I say in one more minute? From this, I could get that theta n hat minus theta naught is approximately the negative L prime theta naught over L double prime of theta naught. We want to show that theta n hat was asymptotically normal with mean theta and variance equal to the Cromie-Rao lower bound. So if we subtract off theta and divide by the square root of the Cromie-Rao lower bound for theta, we want to show that this is going in distribution to a normal 0, 1. So next time we're going to use this expression for this to get us there. So yeah, I'm going to work on a split screen kind of thing next time to try to leave up really important information as I finish the proof. Okay, thank you. And I'm trying not to say please come back every time, but I'm kind of thinking it. So yeah, I'll see you next time on mathematical statistics.